Hi, I'm going to talk about optimism basics, optimistic rollups in general, why I think they're the way forward. First, what's wrong with Ethereum? Why are we offering a solution that is different from what we have now? Scale. Ethereum is great, but it has limited capacity. Limited capacity means we get congestion, we get high gas costs because everybody wants their transaction in. Remember, a few days ago, a Uniswap could have cost you $3,000. Now, why is this? Because every transaction is executed by thousands of computers, and that's a lot of computer space. And those computers can't be required to be too powerful because we want people to be able to run their own nodes. The merge is going to reduce this somewhat. It's still going to be in the hundreds though, and we assume it is still going to be expensive. So, how do we fix it? We don't use L1 for everything. We'll use L1 just as our dispute resolution mechanism. This is like checks. I give you a check. Do you go to court and sue me to get the money? Of course not. Courts are extremely expensive and inefficient method of doing pretty much anything. What you do is you go to the bank, you cash the check. Now, normally, nobody disputes it, everybody's happy. But let's say that I'm evil, and the check bouncy. Now, in this case, you'll go to court, and the court will take my money and give it to you. The fact that courts exist and that I know that if my check bounces, I will have to pay anyway, motivates me to actually make sure that it doesn't bounce, right? That is the way optimistic rollups work. Now, first, what's a rollup in general? We write all our transactions to L1. This means that we have the same availability and integrity promises as anything else on L1. There's a huge number of copies. They all have our data. Changing it, faking it, going to be too challenging. But to calculate the results of transactions, we do it on our sequencer. You can do it on your own if you run a replica. A few computers do it, it's a lot cheaper. And of course, we need to have a mechanism to ensure reported results are accurate. And there are two of them. The first is let's start with zero knowledge rollups because the majority of the talk is on optimistic rollups, of course. Now, notice that this is me talking about our competitors. I may not be 100% accurate, but basically the way it works is you calculate the sequencer calculates a zero knowledge proof of the transaction, and that is expensive. And then this proof can be verified on L1, and this is very cheap. Problems. First, calculating the zero knowledge proof could be something that is expensive, which might limit who can run a sequencer. And the second issue is that they rely on complicated math. Now, it may or may not be possible to run the EVM directly over a zero knowledge. Now somebody is going to tell me, of course it's possible. Zero knowledge has been proven to be Turing complete. You can do anything you can do on a computer on a zero knowledge. That is true, as long as you disregard performance. Remember, Turing complete means that you can do something. It doesn't tell you how fast it is. A lot of very smart people are working on zero-knowledge EVMs. I wish them all the luck in the world. we don't know yet how fast it's going to be. The second issue is that not many people understand this. I mean, the world has probably thousands, maybe tens of thousands of people who can write code for the EVM. Not that many people can do zero knowledge correctly. And this means that not that many people can audit it. It's a lot more difficult to find security holes in it. Now, you could say that this problem is transient. 10 years from now, this won't be an issue, which is true, but now is not 10 years from now. So the other solution, which is simpler, is optimistic rollup. We post the results on L1 immediately, but we have a fault challenge window for other people to dispute them. And instead of relying on mathematics, we rely on economic incentives. If you're the sequencer and you post the correct result, you get rewarded. If you're a verifier and you say, no, this result is incorrect, stop it, and you're right, you get rewarded. Alternatively, if you post an incorrect result or dispute a correct one, you have to pay a penalty. How does this work? Fault challenges. Now, I'm calling them fault challenges. This is the preferred optimism nomenclature. The original name is fraud challenges. We decided to change it because when you use the word fraud, regulators immediately start getting interested, and it triggers them. We don't want to trigger regulators. We want regulators to drink their coffee, sit in their office, and not bother us. So we prefer to call it fault challenge. And how does it work? The first part of it is bisection. You find the step in which the verifier and the sequencer disagree about something, and then you execute that one step on L1, and yes, L1 execution is more expensive, but if it's only one step, one opcode, it's okay, it's not that bad. How does this work? Let's say we're going to have in orange the proposer, in blue the challenger. The proposer says, before we did all the transactions, state 0 is a certain value. The challenger agrees that it is S0. Then the proposer is going to put S7 and say, this is the state after the transaction. The challenger says, you're lying. It is actually S7 tag. It's a completely different value. Stop cheating people. What do we do? And we, in this case, is a contract running on L1. It calculates half of this and says, okay, on L after step 4, was it the same? What is the state? Again, the proposer says S4. The challenger says, no, it's S4 tag. And again, so now we know that the problem is between S0 and S4, right? Cut it again, S2. The proposer says S2. The challenger says, finally, you're starting to tell the truth. It is S2. You have the correct value. So in this case, we know that the problem has to be either after step 3 or after step 4, because they agree on what it's like after step 2. So now we're going to check about after step 3. The proposer says S3. The challenger says S3 tag. You're back to your old tricks again. And now we know that what they disagree on is step 3. And if we can run it on L1, we can find the correct solution. How do we execute one step on L1? Arbitrum, which is our biggest competitor in the field, transpiled the EVM to something they call AVM, Arbitrum Virtual Machine, and they execute one AVM step in their fault proofs, and that's how they work. Optimism, we started with a different technology that didn't quite work, so now we're somewhat behind them, and we are working on a system that would transpile Geth to run on MIPS, and run these MIPS on top, and these MIPS would then would run on top of the EVM. So a virtual machine on top of the EVM. Now, in terms of performance, this looks very, very stupid, right? Performance is going to be terrible, but we are going to run one opcode, so we're not that worried about it. Arbitrum is also working on a similar system to this called Nitro, which is going to use WebAssembly, and we'll see who gets there first. So to put this all together, all the transactions are written to L1. Anybody can verify the state of the blockchain at any point. By the way, if we do EIP 4844 and we start having storage that we're only keeping for a month, we lose some of this, but you'll still be able to know that the state today is correct because of those economic challenges. And the state commitments are probably accurate because as long as there is one honest verifier, it will become the correct value, and economic incentive are aligned with honesty. Now you're going to say, yes, but verifiers only make money if you cheat. And you're motivated not to cheat. So why would anyone run a verifier, right? The reason would usually be because they run their own project on top of the optimistic rollup, so they want to trace the state of the network on their own, or they're a bridge and they allow fast withdrawals, which means that they have to trust the state, so they need to calculate the state anyway. Might as well spend a little bit more of resources and also do default challenges when needed. And where is this all implemented? The sequencer receives transactions direct, and there are two ways it can do it. It can do it as an RPC endpoint. The problem with an RPC endpoint is that it is censorable. So you can also post your transaction on L1. It will be slower, it will be more expensive, but it's not censorable. It means if you post a transaction on L1, then after a certain amount of time, the only way that the optimistic rollup can continue is by incorporating that transaction. Nothing else is valid. And the sequencer decides on the order of transactions. Currently, it's a very simple decision. First come, first serve. Eventually, this might be used to provide MEV, a miner extracted value. And then once we're decentralized, which I admit we are not decentralized yet, Arbitrum isn't either. It takes time. Writing an optimistic rollup is a big job, and until it is done, it's not a good idea to decentralize because we need to upgrade. Anyway, once it's decentralized, this might be decided by an auction mechanism. So essentially, we use the miner extracted value to pay for our network expenses. No blockchain's an island. So far, we have a blockchain. It runs on top of Ethereum, but it doesn't talk to Ethereum. won't work. People already have their assets on Ethereum, and if you reinvent the wheel, they're not going to use your system. So they need to move their transactions from one to the other. Okay, I lied. Blockchains are islands or are like islands. Why? Because the entities that you use to transfer assets are called bridges. And there are two flavors of bridges. The first, which is usually provided by the optimistic rollup company provider, is Trustless. It uses the same decentralized mechanisms as the optimistic rollup itself. But then there are trusted bridges. We'll talk about them in a moment. So you want to deposit, you send your assets on L1 to the bridge. For ERC-20, of course, you use allowances. You call the L1 bridge, and what the L1 bridge does is it locks the assets, it holds them, and sends a message to the bridge on L2. The L2 bridge is then going to mint the equivalent asset on L2. Remember, we run L2 so we can decide what to do with it, but on L1 we have to keep those assets locked so that eventually people trade, move the assets around. Eventually somebody will want to withdraw them to L1. Okay, maybe not. In fact, I hope that they won't. I hope that they stay on Optimism, but people have to be able to withdraw to L1 if they so desire. So we have to do a withdrawal. The way that we do it is you call the L2 bridge. The L2 bridge then takes the asset, burns it, destroys it, and sends a message to the L1 bridge that says, okay, I destroyed this L2 asset because that belonged to that address. Give them back the L1 asset that is equivalent. Time passes, specifically the fault challenge window. Because if I was dishonest, I would try to send a message saying that I burned a bunch of assets on L2 and now they're on L1 and they expect and get a bunch of assets from the trustless bridge. You don't want that. You don't trust me, do you? Well, you shouldn't trust me. That's the whole point of Ethereum. So, but once the fault challenge window passes after a week, the user can claim the transaction on L1. The transaction root, you do that using a Merkle proof, and then the L1 bridge can release the L1 asset that was locked to it in the previous slide back to L2, back to the user. Now, this sounds a bit complicated, right? And slow and possibly expensive. It is. Because of that, there is a different solution which is called trusted bridges. The way that they work is the user sends the assets. It can be Ethereum, it can be ERC-20. We're also working on an NFT bridge on one layer, and the trusted bridge sends the asset back on the other layer, minus a small fee, of course. They need to make money somehow. And the way that this works is that the bridge may pay a little bit to liquidity providers for providing that liquidity, because essentially you get a 7-day loan. So there's going to be a bit of interest. And it can use the trustless bridge to balance the assets. If there are too many deposits on L1 and withdrawals on L2, it can move a lot of assets from L1 to L2, and vice versa if people are depositing on L2 and trying to withdraw it on L1. Those trusted bridges also can only work and can only make their money if the network is run honestly. So they have a huge economic incentive to run their data, to verify that the optimistic rollup isn't cheating them. How to use Optimism? First, you need, of course, to add it to your wallet, deposit ETH for transactions, and then you can play with different applications. Step-by-step directions are available at this URL. You can see it in this QR code. Exercise. This is from our GitHub. Run your own application on Optimism.